Hi, my name is Patrick Akpan, and I'm here to make a presentation on methodology for developing and validating representative process models for coal-fired power plants. A short note on the authors. Dr. Patrick Akpan, being myself, I'm a lecturer at the University of Nigeria, Nsukka, Department of Mechanical Engineering, and Associate Professor Fuls is also a lecturer at the University of Cape Town, South Africa, Department of Mechanical Engineering. We're both experts at the modeling of power plant processes, and we do a number of things on energy and power systems as well. Our profile is there for you to read. Introduction. Energy mix modelers often try to justify the use of large amounts of renewable power systems in an electric grid by trying to quantify the emissions impact, the emissions that is reduced from the power plants once you introduce renewable systems in. And one of the ways that they used to study this emissions impact is by first of all understanding the thermal behavior of the power plants. So oftentimes you will see energy mix modelers grouping power plants in a particular power system and giving them a certain kind of characteristics, just because it's very difficult to understand or very difficult to determine the thermal performance of each given power plant. Modeling and simulations offers a significant opportunity when it comes to trying to understand how a power plant behaves, and it's because it's very cost effective. You don't have to physically test any plant. All you just need to do is set up your models and calibrate them with the existing data and validate them. Usually such models would require a proper understanding of the process parameters along the various points in the power plant at different conditions as well, both full and varying load. And sometimes it is difficult to get these information, especially the ones at other loads. So it becomes important for one to find some credible means to be able to model these power plants, hence these studies. And now the objective of this particular study is just to describe a methodology that is used for developing and validating a credible process models that can be used for investigating the thermal performance of various types of coal power plants at various loads with just the knowledge of a few input parameters. Now, the methodology that was used in this particular research, first of all, we had to identify the important parameters that we would call the minimal parameters that will be used for modeling the representative plants. So the parameters that were identified were the throttle steam temperatures, the throttle steam pressure, the condensing pressure, and the number of feed water heaters in the cycle. Now, once these parameters are understood, and equally the degree of reheat, meaning if it's single reheat, double reheat, or non-reheat. So these are the input parameters that are required in this particular method. So the next thing is to select typical layouts for the different kinds of architecture. So for a non-reheat power coal-fired power plant, we selected this particular architecture with one high pressure turbine and one low pressure turbine with a double flow, and then with 6 feed water heaters in it. So this particular layout was modeled using a software called VirtualPlant, EPPEI VirtualPlant. That's the software that was used to model this particular type of plant, and this is how it looks like in the software. For the single reheat, this particular type of layout was selected with one high pressure turbine, one intermediate pressure turbine, and one low pressure turbine with a double flow. Also, this particular layout has 6 feed water heaters as well, with extraction points from all the turbines. and this particular layout is represented using this in this particular format. For the double reheat coal-fired power plants, the layout that was selected is something that looks like this, and with a high pressure turbine, an intermediate pressure turbine, with two intermediate pressure turbines and one low pressure turbine with double flow. For the double reheat, we had to select 8 because that's typical of what you would see in a double reheat power plants, from 8 upwards, because they are usually large inside when it comes to power output. And we represented this layer in the software with this particular configuration. Now, once we selected the input parameters, which are the throttle temperature, pressure, the number of feed water heaters, the degree of reheat, and a host of others, the next thing to do is to look at the computation, how the computation is done. So the computation was done in 2 different phases. Phase 1 actually had to do with the development of a credible valve wide open, or what you would call full load heat balance. Now, a heat balance diagram is just a diagram of the process components and showing the process flows, the inflows and the outflows from one component to the other component in the power plant. Then the second phase had to do with actually calculating the performance of the coal-fired power plant at the different load conditions, and this we had to do with the help of a VirtualPlant software. The first one was actually done with the use of an Excel spreadsheet that is embedded, that has steam tables embedded in it. Now, the computational steps used in phase 1 are shown on the slide. The first thing that had to be done was to determine a final feed water temperature methodology and an extraction pressure method. Then the next thing was to determine the reheat pressures for the cycle and determine the enthalpies up to the last step, which is to complete the cycle check. So these were the steps that were used in determining or in computing the various key process parameters that were needed to develop the representative process models. And for the various power plants, we had to look at a wide spectrum of power plants. We had to look at the different components, parameters that are used or that are available in both literatures and in existing power stations. And I must say that we really got a lot of help from Eskom power plants, Eskom Power Holdings. Eskom is the largest utility company in Africa. They have a lot of coal-fired power plants in their fleet. So these are some of the typical values you would see, like you see, for instance, the efficiencies of your high pressure turbine, which is item number 5. You see those values, and then you see the values for the typical extraction line pressure drop. So these are typical values that have been extracted to represent the various values that one would see. Now, after selecting the process parameters and the components parameters, the models were set up in the VirtualPlant software using this particular selection method. So for the boiler, we had to use the simple boiler calculation method. There was no need to use an air preheater. For the steam turbines, the high pressure turbine, we had to make use of the variable pressure approach, and we used for the turbine efficiency model, we had to use the constant efficiency model, meaning that we assume that the efficiency of the turbine is constant along the parts of the turbine and for various load conditions. So these were essentially the parameters that were fed into the VirtualPlant software. Now, before the phase 2, the beginning of phase 2, towards the end of phase 1, one had to run the model at full load, get the results, and validate the results. So once the results for the full load is validated, then we proceed to phase 2 if it is satisfactory. So for the phase 2, we simply carry out a varying load analysis, and this is done with the help of the parametric feature of the VirtualPlant software. Now, the parametric feature allows you to carry out parametric studies where you change different variables. Excuse me, you change different variables and you see the effect on the results. So, if you look at what's on your screen, for instance, now the variables that are here, first of all, the gross generation, which is representing the load factors. So you can see from the generation of 60 megawatts up to generation of 200 megawatts. Of course, because we understand that as generation decreases, so does the condenser back pressure decrease. So we had to take care of that by using one of the models that was published by us some time ago. So with the help of that model, we're able to generate the condensing back pressures that we used as the variables here. So the key results that we looked at here, if you look at the thing that was highlighted there, you can see the TCHR values that were determined at the various the generation levels. So the simulation is done with the help of the parametric study feature. Now, the methodology that has been presented so far was validated using data from 11 different power plants that are situated in South Africa. Now, the key process parameters that were taken from the power plants are the throttle temperature represented as PTHR, the throttle temperature, the condensing temperature, and the cooling technology, which you can see highlighted in this particular region. So these were the input parameters that were taken for these particular plants and fed into the methodology, and then the results that were generated from the results that were predicted from them were now used to compare with the actual data from these plants. You can see that we used 2 non-reheats, that's plants 1 and 2, and then we used about 8 single reheats and 1 double reheat plant. Now, in discussing the results that we're getting from the model, it's important to note that for any given power plant, there are so many process conditions that can be talked about. You can talk about the reheat pressure, you can talk about the throttle temperatures, you can talk about the final feed water temperatures. There are so many things that can be looked at, but in this particular presentation, we're going to be looking at just a few of them. Now we begin with the low pressure turbine exhaust condition. This condition is very important for us to examine because for most power plants, you don't want the power plant to operate in a condition that is having a steam dryness fraction that is below 0.85. And this is done to protect the LP turbine. So if you look at the results of the predicted results of our model and compare it against the plant data, you can see that in all cases the exhaust condition is above 0.5. That is the LP dryness. The dryness fraction is 0.5. That's at full load condition. Now, when we look at the value at varying load conditions, what we see here is that as you begin to reduce the load from 100% down to about 40%, that the dryness fraction of the steam from the LP turbine increases in the same manner with which the plant data increases. So if we look at the plant 0, which is representing the single reheat plant, you can see that the results that are predicted here are very close to that of the plant data. Now, when we look at the figure D, which talks about the accuracy of the LP turbine exhaust steam quality, when we look at it for all the 11 plants that were looked at, both the non-reheat and the single reheat and double reheat, we can see that for all the different load conditions from 100% to 80% to 60% and the next thing is the main steam flow. This is very important because it enables you to size accuracy of the model. So you can see that above 95% full load condition, telling us that the
our model
results,
only deviates
the predicted
by
results
about
closely
5%
match
when
those
it
of
comes to
the
predicting the
plant
LP
data.
turbine.
Now, when we look at
steam
it at
condition.
various load conditions for both plant C and O, we see that the steam flow the steam mass flow decreases with a decrease in the plant load factor. This is expected because a power plant that produces power that is lesser than the value with which it was designed, you would expect that the steam flow will also decrease. Now, when we look at the accuracy, once again, the accuracy is very, very good, as you can see for most of the plants. Unfortunately, the accuracy for the plant C at the 40% load is slightly close to slightly below 84%, and it's slightly below 84%. Now we look at the next parameter, the final feed water temperature. We can see that once again the results predicted closely match those of the plant data. And we look at the final feed water temperature at different load conditions from 100 to 80, 60, and 40. The predicted results once again closely match those of the plant data. And when you look at the results for all the plants at a go, and you look at it for the various load conditions, you can see that the minimum accuracy that was seen there is about 92%. So you see a drop of a deviation of about 8% seen across board there. Now, for the most important parameter, which is the heat rate, which helps us to examine the overall thermal performance of the plant, one can see that once again the predicted results closely match those of the plant data, and you can see that the heat rate increases with as the load begins to increase. This is expected because at lower loads, the thermal performance of power plants generally decrease. We see that for the plant C, which is representing the non-reheat, and we also see it for plant O. So when we look at the accuracy here, the minimum one that is seen, which is in this case for plant F, is at the full load conditions about 93%, meaning that the highest deviation that is seen across all the plants for when it comes to predicting the heat rate, it's about 7%. In summary, when we look at other parameters, including the ones that have been mentioned, one can see a summary of the deviations that are seen for all the parameters. So the most important one to look at is the last one, which is the TCHR, which enables us to examine the overall thermal performance of the plant. One can see that for over 70% of the case studied, you can see that the deviation is below 5%. In conclusion, one can safely conclude that the method presented in this paper is suitable for developing representative models for coal-fired power plants. And this methodology, the models that have been developed that have been developed with using this method can be used to set up the steam cycle process models for different power plants at full load, and also for investigating the overall thermal performance of the plants at various load conditions, with results giving you deviations that are below 5%. We would like to appreciate the following organization for the funding support that was given for this research, and I would also like to appreciate the following people for their support throughout the research. Thank you, and if you have any questions, open to listening to your questions. Thank you very much. I hope you enjoyed it.